reason why we have this holding lugs with us. These are integral part of this part just for the purpose of holding this whole block onto the holding fixture. Now we have a plate below that's going to, on which this particular stock will be mounted, and this particular plate has got a pneumatic arrangement where we are going to hold, it's like vacuum, so we're going to hold the center portion on vacuum. We're going to have the edges all locked up using M8 screws, and then the center portion is going to be held using vacuum. So we have got the holding plate. We also have the stock, which resembles basically a rectangular block with the holes through which I'm going to put my Allen screws and bolt it to the holding fixture, and then I'm going to switch on my vacuum to hold the part so that it doesn't lift up and then cause warpage while machining. Okay, let's switch off for a moment my holding plate and just keep the stock and the part on. And we are going to machine the entire thing now using iMachining 3D and swarf machining. You will also notice that I have colored the rib tops with a particular color, and this is for doing easy selection, which we are going to see in SolidCAM. It's a new thing where we're going to select surfaces by their color. So it becomes much more easier to select it so that you don't spend a lot of time in selecting this surfaces. Okay, let's start with new milling. Yep. Yes. Okay. So let me. We're going to use a Burmac, the Spanish machine, and with a Siemens 840D controller. It's a head type machine. So let me select Siemens 840D and set my coordinate system top of the center. Flip around Z. That should be my first coordinate system. Okay. Put some values up here, 150, 25, okay, accept it. So we have our first, thing done already. We have set the coordinate system, and you can see that the target and stock are already defined, although I don't know what they are. We can always go back and change this. Now, since we are going to use iMachining, I need to set some of my parameters for iMachining, like the machine. Then we have the material, etc. So I'll accept this. I'll exit for a moment because I just need to change the version. Okay, just a moment. Again, please. Okay, let me open the same part. Okay. I have now defined my coordinate system and stock and part, but we just need to recheck. So I'm going to check the stock again. A lot of solids have been selected. We don't need them. I'll unselect all, and I'll only select this particular CAD data with a tolerance of 0.1. Okay. Let me hide the stock because I don't need it anymore. I'm already done with it for the moment. Now I need to define my target. So I'm going to define, again I'll unselect all of them, and I'm going to select only the main part. I'm not going to select the lugs because I'm going to add the lugs later on in the operation only when I need them. Otherwise, my target doesn't include the lugs. Okay. Right. So we have already done the target, stock, and coordinate system definition. All we now need to do is to select the right machine. So we're going to select Burmac. It's the head gantry type machine for such big parts, which has a maximum spindle RPM of 12,000, a maximum feed rate of about 12 meters, and a spindle power of about 22 kilowatt. We're also going to use an aluminum 6061T6. This is the aerospace grade aluminum. So we are going to use these two things, the machine Burmac and 6061T6. Okay. So I've already set the parameters for iMachining. Now what I'm going to do is I'm going to switch on again my stock because now I'll need it for my first operation. My first operation is actually going to be clearing out the material, not from inside but from the outside. I need to remove the material from outside. So I'll add a 3D iMachining. In this case, it's not going to be the target because I need the lugs back with me. So I need to define the material other than the lugs. So I'll just hide for a moment the stock and define a new target. This is going to be a local target. It's only going to be valid for the function where it is selected. It's not a universal target. So I'm going to select all the lugs. Selecting all the lugs together. These will form the part of the part so that we don't end up removing the lugs. It's needed for us. Okay. I'll select the tool. For this operation, I'm going to use a 20 millimeter end mill. 60. This is 50 and 35. It's a 3-flute end mill. 45-degree helix. Let me change it to 35 degrees. Holder. I'm going to use a HSK 63 holder. That's how my tool looks like. Okay. Right. Now let's get the stock back again because in the geometry, since I want only the outer portion to be machined, I need to now tell to iMachining that I just want the outer area to be cut. So I'll define a working area. Constant Z. Go into the wire frame and select the innermost curve. Again, constant Z. Okay. So we have got two curves selected, the outer and the inner. So the area between them is the area to be machined. And the outer curve can be marked as open because the tool can approach from outside. Okay. Technology wizard, we are at level 6. And these are the parameters that iMachining has calculated by itself for level 6 dynamic parameters. Technology, I'm going to keep an offset of 0.8 or 1 millimeter. A tool path tolerance of about 0.2 because I'm just going to keep about 1 millimeter offset, so 0.2 is good enough. Okay. Once that is done, let me save this operation, go out here and calculate it. So it'll take about 20-25 seconds. Okay, so calculation is all done. If I look at the tool path, let me switch off the stock now. That's very nicely done from the outside. It's not machining the inside at all. So if I run the simulation, solid verify, This is how it looks like. The lugs are as they are, they're not cut. At this level and below, I have the screw. So the upper area, 3-4 millimeter, can be cut, no problem. All right, so we have the first roughing that's done for the external. Now, before I start doing the opening up the internal pockets, I actually have to rough and finish out these ribs. These ribs you can see are not on one level, but they are changing. They have a shape to themselves. The ribs have to be roughed and finished. I can't leave it to later because once I scoop out the material from here, I'm actually going to have a very weak edge or very weak rib on which if I put my cutter and run it at even a speed of about 1000, it's going to vibrate, it's going to bend, probably it's going to break, even it's going to damage the part and the tool itself. So the ribs have to be roughed and finished even before I scoop out the material from the center. So that's going to be my second operation. So I'll add a 3D HSR, sorry. And here I don't care if I'm going to use the target model or the local model that was used for iMachining. So because I'm going to be within the part. Okay. Sorry. I'm going to select a 10 millimeter ball nose end mill because it's going to be on a very small area. .45 millimeters out of holder. 25 is my cut length, 2 flute. Select the tool, constraint boundary. Okay, sorry, this has to be contour. We add the tool again. 45, 25, 2. Okay, that's done. In the constraint boundary, because I want to cut only the ribs, I have to define a boundary that's including only the ribs. How do I do that? Simple. I'll create the boundary manually using the selected faces. The faces are now going to be selected, but since there are too many, I can't select them manually. It's going to take a lot of time and a lot of effort. So I'm going to use the new function of SolidCAM to find the faces based on a typical color. So the moment I pick a color, SolidCAM records the RGB value of that particular surface, and then when I hit find face, it recognizes all faces with a similar RGB value. So it's now selected 66 faces in less than a couple of seconds with the same color. So it's almost selecting all the ribs. It selected all the ribs. And I would like to give an offset of about 1.5 millimeter and create the boundary. So if I click on show, you can see that SolidCAM has nicely made the boundaries for machining only the rib tops. Okay. Onto the process. Keep about 0.5 millimeter for my finishing. 0.1 as my offset. Step down of about 0.7. A minimum offset of 2 and a maximum step over 3.6. Refine corners. No adaptive step down. And ramping of 5 degrees with 1 millimeter offset. Profile. Retracts minimum. Clear the surface by 10 millimeters. All right, that's all that's needed. Save and calculate. All right, the calculation is done. Let's switch on the toolpath. That looks nice. If I now run, let's say the simulation, solid verify, switch off the holder and run the toolpath. You can see that it's machining just the rib tops. Of course, instead of using a ball nose, I could have used a bull nose or a flattened mill. I prefer to use a ball nose. All right. So it's done the roughing of the rib tops. All I need to do now is to finish the rib tops. So what I will do is I will add another operation for HSM and use the 3D constant step over. The tool remains the same. The drive boundaries is also the same as roughing. In the constraint boundaries or the part boundary, I'll have to recreate the same thing. Define, pick from model, find faces. Okay. Offset of 1, that's where my boundary offset is. Okay, in the process, I'm going to keep about 0.5 millimeter side step both on the vertical and horizontal. Okay, link, retract 10 mm. Let's save and calculate this. Okay, that's done. Let's check how the toolpath looks like. So that's how my toolpath is going to look like. It's running only on the ribs, doing nothing else. Okay. So once we have roughed out the outer area, we have roughed out the ribs, and we have finished the ribs, it's now time to get inside to the pockets. So I'm going to add another iMachining operation. And this time I'm going to use a different tool. I will use a 20 or 1.5 bullnose. I have a corner radius there of 1.5. 50, 35, 3 flute, holder, HSK. All right. The geometry, however, cannot be target. It has to be the model again, because otherwise it's going to cut off the lugs. So we have to use back the same part that was used earlier for roughing. Okay, level 6, offset of 1 millimeter. I don't want to keep very less offset because of the issues of warpage. So I would like to keep some material and then gradually remove that material using swarfing to overcome the issues of warpage. Okay, let's save this and calculate it. This would take about a couple of minutes of calculation because it's a pretty large part. Okay, I think I made a small mistake here. That's the reason it's taking such a long time. Let's kill this process and start it again. I gave it extremely tight tolerance to calculate, and that's the reason why it's taking such a long time. Because since it's a roughing toolpath, I don't have to be so, the tolerance need not be so tight. If you look at what's the tolerance that I've used, going to the technology, it's 10 microns. It's too much for this toolpath. 0.2, that's what I gave earlier for the other toolpath. And let's calculate this. This should take about a minute and a half to 2 minutes. Sorry for it. think we have hit up some issue. Let me again restart this. Okay, sorry for that. Okay, for some reason it's not doing it. Let me see what was the issue. It's fine. So it's fine. Yep. Everything is fine. Anyway, we'll just suppress this for a moment. And let's go and check the swarfing. So once we have the roughing done, I'm going to open another part and I'll show you what that result looks like. So in the meanwhile, just let's go on to the swarfing part. So once we have the roughing done, we need to finish up these walls. To finish these walls, there are many ways. Some people do it in 3-axis. They use a disc type of cutter to overcome the undercut and finish the part. Some people do it in 5-axis, and in 5-axis you can go like using the down steps, or you could use a single cut. Just use the flute length and cut with the side of the tool the entire part in one go. That's possible, and generally that gives a much better result, a much better surface, and the fastest machining time. Now in SolidCAM and in swarfing, you've got this advantage that you could directly create the toolpath without having to create much of a geometrical modification. So you directly select swarf in the geometry, select the swarfing geometry. So let's select the faces and this face. Okay, and the floor will be up here. These are the surfaces that will act as a floor geometry. Okay. The tool, since it's going to be a very small depth, I'm going to use a smaller tool. I'll select an 8mm ball nose. I'll create an 8mm ball nose. 28mm cutting length, 2 flute. Okay. Select. Entry and exit safety distance of 10mm each. I would like to cut it inside. No changes to the tool axis control. We will see some options on this when we do the machining. Okay. Let's save and calculate this toolpath. The calculation is also pretty quick because it doesn't have much of parameters to deal with, because most of the things are automized inside. So let me run the simulation. So that's how my tool will enter. Of course, what I can do is, okay, before we start the simulation, let me put in some leads and links. So I'm going to put a link, a lead in with 1mm height, and a lead out also with 1mm height. Okay, save and calculate. Let's run the simulation. So we have a nice lead in and a lead out now. Okay. There's not a much nice thing happening in the corner. Okay, we noticed our first problem. Goes to the second one. It's also not a pretty sight. So it's giving me a couple of issues. Okay, let's fix the first issue of this tool dancing around the corner. It's pretty simple. Go to tool axis control, and I'll minimize the rotation axis changes, and I'll calculate it. Now let's run the simulation. We should have a much better tool path, especially in the corners. Yes, it's much better. Yes, nice. But now we have a couple of issues here. You can see that my tool is trying to tilt and then straightens up to continue to do a better job. So we do have problems in between which need to be fixed immediately. So how do we do that? We know that we have an area up here that's having a problem. So let's say from this point onwards to somewhere up to here. So what I'm going to do is, this is where SolidWorks comes into picture. I'll create a 3D sketch and drop 3 lines, straight lines. One over here, another one over maybe here, straight line. The length doesn't matter because what matters is only the direction of those lines. Okay, so I have 3 lines, so I'm going to edit this toolpath. Go to the geometry and select tilt lines. So I'm going to select 1, reverse, okay, 2, reverse, okay. I can't the surface pretty nicely, so let's reverse the direction. 4 more lines and we're done. Reverse, okay, and then we have this one, reverse, okay, okay, and the last one. Done. Okay, let's save and calculate. Okay, let's simulate now. So now if I look at the simulation, things should be much better. Right. Okay. I can see that it's not trying to tilt itself. It's following my instructions of taking these 3 lines into account while it's moving around the surface. Now these problems can occur mainly because when you try to work them on imported geometry, sometimes surfaces can have issues. Now instead of modifying the entire surface geometry, we only modify the tilting geometry in such a way that the tool doesn't do what it wants. Now you could have not just 3 curves, maybe 5, 6, you could get a much better. Now I don't want to remove the going to add 3 layers of 0.25 each. So it's going to remove 0.25 material at every pass, and I'll blend a spline between these 3 tool paths. Okay, that's done. If you look at the tool path, this is how it looks like. So I've got 1, 2, and 3, each having 0.25 step over. So I'm going to gradually remove the material. I'm not going to remove the material in one go. It's going to be slowly shaved off. Now this, instead of going in one go, if my customer would like to take number of cuts on the wall and not just single axial cuts. That also is possible. I'll edit this. I'll go to the layers. I'll say this is 1. And here I'll say I want 10 cuts on the wall. And they have to be morphed with the upper curve and lower curve. And I'll calculate this. Right. Now if I look at this simulation, on this toolpath, you can see that it starts from the upper edge and goes down all the way down to my lower edge by number of passes. So the entire width of those surface is divided into 10 passes, 10 equally spaced passes. So I have a possibility to do both. I have a possibility to add axial depth of cut. I also have the possibility to add radial depth of cut. Right. Let's make this again what it was. So roughing, this is 1, this is 3. Calculate. Okay, so we have this toolpath. Now I have finished the wall, and to some extent a couple of passes on the bottom surface. The bottom surface still has material. We still have 1 millimeter of material on the entire bottom surface. Now what I'm going to do is I'm going to create another kind of a toolpath that will create the machining of the floor surface. So I'm going to add simultaneous 5-axis milling parallel to surface. My drive surface is this. This is the surface that I need to machine, and my edge surface or the tool has to be parallel to all these surfaces. Okay. This, and this. Okay. So we've selected all the surfaces. If I click on show, all the surfaces are selected. I'm going to use the same tool, 8 millimeter ball nose, levels, 10 and 10, and we're going to create some 20 cuts, and step over between each of the cut is about 0.5 millimeter, and it's going to be a spiral. Okay, I'm going to change anything with the tool axis control, and in the geometry I like to add the tool radius. Let's calculate. Okay, so we have a tool path that runs, but it's not yet checked for gouges on the side surfaces. So we need to do that. What I'm going to do is, first of all, I'll reduce the step over to about 0.35 and go to the gouge check, switch on. We're going to see a new type of gouge check today. I'm going to check against the check surfaces, and the check surfaces are basically these surfaces. I'm going to tilt the tool with maximum angle. However, there's a new thing that's coming up in SolidCAM in the tilting, and that's called automatic tilting. So SolidCAM will decide where it has to use tilt, side tilt, and where it has to use lead lag angles to avoid gouging. Sometimes it could use side tilt, sometimes it could use lead lag, sometimes it could be a combination. So a single toolpath can have all these 3 combinations possible using the automatic tilting. All right, let's hit save and calculate. On the simulation. Okay. As we go closer, it's going to be much more visible. So let me go onto the side. And as it goes closer to the surface, you'll see that the tool will start tilting. Yeah. So as it goes closer and closer to the surface, the tool starts tilting. can see that the tool is using the all the three options of lead, lag, and side tilt. So it applies depending on the situation what it needs to apply. So at some point it could use a side tilt, at some point it could use the lead lag angle. So it's you use a combination of all the three options available to it. All right, so we have done something here. Let's do the same thing, the swarfing also on the other side. So I'm going to copy this, paste it, edit, and I'll select a new geometry now. Okay, for this surface here. All right, this is done. The floor surfaces, of course. The advantage in using swarfing is it's very fast, and you can get extremely fast results even on the machine. You don't have to go multiple depth of cuts and all those things. So that's the major advantage that you find with swarfing. So I have my floor and I have my part surface or drive surface. I don't need to do anything else. Simply hit save and calculate, and I'll still get those three passes that I had defined. You can see that this particular face out here has got a positive draft, so it's using the side of the tool to generate a positive draft. Then the second cut, and the last cut. Okay, so if I take this, all those three operations, let me switch off the, okay, it's off already. And if I take both the swarfing operations, let me first set the machine setup, sorry. Okay, control, simulate, machine simulation. Okay, this is how my machine would look like. It's a gantry type machine, head. Switch off the machine slide and run the toolpath slowly. Go to the next one, simply jump and run the swarf. Okay, that was about the machine. And if you look at the output coming out from the software, the G code for Siemens. Okay, and this is the output for Siemens. We use the ternary function for the RTCP movement. And if there's a 5x and then the output, the vectors in x, y, and z, and Siemens does the calculation for the angles. We also can output obviously the angles, but this post-processor currently is equipped to handle vectors. All right, so I come to the end of the webinar, although it was not a great one because I could not calculate one of the main tool parts for iMachining, but we will be having a recording of this webinar, the one done before where this tool part was calculated. You can have a look on SolidCAM's website. Maybe by day after tomorrow, these webinars would be up and running. So if you have any questions, please ask me the question. If you can't think of a question and you would like to ask a question later on, you could write to us, and we'll be more than glad to help you. Okay, I believe there are no questions. In case you can think of some question and would like to ask those questions to us, please feel free to write to us, and we'll reply it as soon as possible. Thank you very much for attending this webinar. Have a nice day.